Welcome everyone. In this video we're going to be talking about hybridization and hybridization, which falls under Valence Bond Theory, will help explain some indiscrepancies that we have with regular VSEPR. One of the issues that arises is that the number of partially filled or empty atomic orbitals does not predict the number of bonds or orientation of bonds. For instance, carbon, when you look at the electron configuration, it would predict that you would have 2 or 3 bonds that are 90 degrees apart, rather than what you actually see for carbon bonds, which are usually that it can make 4 bonds and that they are 109.5 degrees apart. So to adjust for these inconsistency, it was postulated that valence atomic orbitals could hybridize before actual bonding would take place. And what we're going to see is that hybridization is the mixing of atomic orbitals. So one hybridization of carbon would be to mix all the 2s and 2p orbitals so that you can get 4 orbitals that point at the corners of a tetrahedron. In other words, this helps explain how carbon forms a tetrahedral structure. As you can see, the observed reality of carbon is that carbon has 4 bonds, and that the angles are 109.5 degrees to each other. When you look at carbon when it's unhybridized, and you can see that here on the left, it would not predict this structure. It might predict that carbon can make 2 or 3 bonds rather than the 4 that you see with the tetrahedron. So the main concepts of the valence bond theory is, number 1, the valence electrons of the atoms in a molecule, they reside in quantum mechanical atomic orbitals. The orbitals can be either s, p, d, or f orbitals, or they may be hybrid combinations of these, which is what we will be talking about. So that's the first concept. The second is that a chemical bond will result when these atomic orbitals interact, and that there's going to be a total of 2 electrons in the new molecular orbital. The electrons must be spin paired. I'll give you an example. I'll give you something simple. Hydrogen is diatomic. It only has an s orbital, and when a hydrogen interacts with another hydrogen, there's going to be an overlap between the 2 orbitals, and in that region of overlap is where you have one electron spinning one way and the other one spinning the other way. That's what they mean by spin paired. And that area of overlap is where the bond takes place. That's where the sharing of the electrons is going on. The third thing is that the shape of the molecule is determined by the geometry of the interacting orbitals. You'll learn that if you have 3 electron domains, you'll see that the spacing, they're going to try to get as far apart from each other, and you'll form a trigonal planar structure. Again, if you have 4 domains, you'll see a tetrahedron will be formed. So the shape of the molecule is determined by the geometry due to interacting orbitals. And that's part of VSEPR theory that we've mentioned before. So what is a hybrid orbital? Hybrid orbitals are formed by the mixing of atomic orbitals to create new orbitals of equal energy called degenerate orbitals. This will be a very important word. Degenerate, you'll see, is orbitals that have equal energy. So what happens is when 2 orbitals mix, they will create 2 what we call molecular orbitals. If it's 3 orbitals mixing, they'll form 3 molecular orbitals. I will show you the difference between an atomic orbital and a molecular orbital in just a moment, but the theme is that if, for instance, 3 atomic orbitals interact, they will form 3 molecular orbitals. So there's a pattern here that we will witness in a few minutes. So hybridization, like I said, the reason it occurs is that atoms hybridize their orbitals to maximize bonding, because the more bonds and the more full orbitals that are occupied by electrons, the more stability that the molecule will have. And hybridization will be used to maximize bonding, which in sense will increase to more stability. Now, hybridizing is the mixing of different types of orbitals, in the valence shell to make a new set. And again, here's the word degenerate orbitals. The hybrid orbitals will have equal energy. So how do we make these combinations? Well, I'm going to show you the ones that are listed here. SP is a hybrid between an S, which is a spherical orbital, and one of the p orbitals. SP2 is an S with two of the p's. SP3, just like it says here, is an S with three of the p's. And we also have SP3D and SP3D2. At the end of the video, I will show you that the shapes and the hybrids have a correlation. Okay, for instance, SP you'll see is the hybridization found for a linear molecule. At the other extreme, SP3D2, you'll see that that's the hybridization found in an octahedral electron geometry molecule. Now, one thing that's very interesting is that the same type of the same type of atom can have different types of hybridization. I'm going to actually use carbon throughout my examples. You'll see that carbon can either sp hybridize, okay, when carbon forms linear structures like in carbon dioxide. It can sp2 hybridize, which I have an example to show you with that. And one of the most common forms that you'll find carbon is in the sp3 format. So the same atom can hybridize in multiple ways, and I'll use carbon as an example throughout this presentation. So the number of standard atomic orbitals combined is equal to the number of hybrid orbitals formed. This is what I mentioned earlier. So if you combine a 2s and a 2p, you're combining two atomic orbitals. As a result, two atomic orbitals will give you two molecular orbitals. When they hybridize, the s and the p will give you two sp hybrid orbitals. You'll see how the s and the p merge and become one blended orbital. One thing to note is that hydrogen cannot hybridize. Hydrogen only has one orbital, a 1s orbital in its valence shell, so carbon will never be able to hybridize. So as I mentioned earlier, the number and type of standard atomic orbital, when they combine, it will determine the shape of the hybrid orbital. Okay, so that's a theme that we'll be encountering as we go along. The particular kind of hybridization that occurs is the one that will yield the lowest overall energy for the molecule. In other words, what we mentioned earlier, that the more hybrid orbitals that we can make, the more bonds that will result. At the end, it ultimately leads to more stability of the molecule. So here is carbon when it becomes sp3 hybridized, and I'm going to show you a picture in a moment. But you're going to see that the way this is drawn, that carbon can make up to 4 bonds here, okay? This is an sp3 hybrid, and let me show you how this is formed. If you look here at this picture, you have the s orbital and the 3 p orbitals, the px, py, and the pz. There are 4 atomic orbitals here on the left. So what's going to happen is the s and those 3 p orbitals are going to merge. And remember, 4 atomic orbitals are going to form 4 molecular orbitals. So the first one is here. Here's the second. These are the 4 molecular orbitals that result from the 4 atomic orbitals blending together. Notice that the purple color will represent the hybrid. Notice how it's a mix of an S and the P getting together. In this case, the 3 Ps. Notice how they all point at a different corner of a tetrahedron, which is shown by the triangular outline. So when you arrange those 4 and you combine the 4 of them together and you superimpose it, you get the overall shape of a tetrahedral molecule. The arrangement of those electron geometries there, of those domains, is 109.5 degrees. So what happens is that carbon has 4 atomic orbitals, the s and the 3 p's, hybridizing and forming 4 molecular orbitals. And if you are a tetrahedral electron geometry, your hybridization will always be sp3. Okay? Here's how it happens. I wrote a little something here. Here are the atomic orbitals before they got hybridized. Notice I did this according to energy. The S is on the bottom, the P is at the top. Notice that the 3p orbitals are at the same level because they have the same energy. You could think of one as the px, the py, and the pz, each line. And what happens is those four are going to get together, so that S and the 3p's are going to combine. And when they form, the four atomic orbitals combined, they are going to form four molecular orbitals, as you can see here. Notice that as they hybridize, the energy is intermediate. Okay, it's between the S and the P. That's why you see it here towards the middle. And notice that the four atomic orbitals will form four molecular orbitals. Each one of these is sp3, 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 and sp3. Notice they all have the same amount of energy. It's intermediate between the S and the P atomic orbitals. And that's what we mean by degenerate. Those four hybrids will be of equal energy, which is degenerate. So this is what it would look like after sp3 hybridization takes place. You'll have an atom with four electron groups around it, which is a tetrahedral geometry. Angles will be 109.5. Okay, and the atom will use the hybrid orbitals for all bonds and lone pairs. Okay, here you're seeing all bonds, but a molecule such as ammonia, which has an electron geometry of tetrahedral, that molecule is sp3 hybrid because it has four electron domains. A domain can either be bonding or, as you can see here, it can also have lone pairs. So when you look at the central atom, whether it's bonding or non-bonding, such as lone pairs, if there are four domains, such as ammonia, okay, that would be an sp3 hybrid central atom. So the nitrogen right there is sp3 hybridized. Now, let's look at bonding with the Valence Bond Theory. So according to the Valence Bond Theory, bonding takes place between atoms when their atomic or hybrid orbitals interact. We mentioned that earlier. There's an overlap between the two. As you can see here, here's the overlap here between the carbon and the hydrogen. Okay, notice the hydrogen doesn't hybridize. It's still represented in green, whereas the carbon is in purple because it's been sp3 hybridized. There's the ammonia molecule that I drew with the lone pair here. Okay, here this would be just methane. So notice the overlap between the hybrid, between the two atoms is where the electrons are actually being shared. So to interact, the orbital must either be aligned along the axis between the atoms, which would be what we call a head-to-head overlap or a sigma bond, or you might see that the bonding might be parallel to each other and perpendicular to the interatomic axis, which when you have a side-to-side bond, that would be a pi bond. Okay? So again, at the end of the day, the bonding is going to be the overlap between the two orbitals. Now let me show you what an sp2 hybrid orbital looks like. In an sp2, and one s and two p's are going to get together. Okay? The other p does not get involved. It remains unhybridized. So if I have three atomic orbitals getting together, here's one, here's two, and here's three, okay? Three atomic orbitals means I will make three molecular orbitals represented in purple, and notice how they are oriented in a triangular arrangement. When you merge these three together, you form this resulting structure when they overlap together. So sp2 hybridization creates a trigonal planar electron geometry. Okay? Now, one of the p orbitals remains unhybridized. Let me show you that. So here we have that diagram I did before. Notice here you have the three atomic orbitals merging. These three will form the three hybrids you see here in purple. They're degenerate. They have equal energy. But one of the p's remains unhybridized. Okay? You're going to see that that unhybridized p plays a role in doing a pi bond, which would be participating in a double bond. So hybrid orbitals, notice, will overlap on axis with orbitals from other orbitals. So the hybrid orbitals will actually, like we saw before, there'll be overlap with the other atom. The unhybridized p orbital will always overlap sideways or side by side. That unhybridized p orbital is the one responsible for forming, in this example, the double bond. And you'll see that that unhybridized p orbital is the one that participates in what is called a pi bond. So if you look here, you can see that the carbon has 3 domains. So it's sp2 hybridized. Notice that it forms one bond here with the hydrogen, that's a sigma bond, another one here, and a sigma here with the oxygen. Now remember that unhybridized p orbital. So notice I circled 3 sigma bonds, but there's a double bond between the carbon and the oxygen. Notice that the p that was never hybridized, notice it still retains its dumbbell structure, is going to do a side-to-side overlap with one of the p orbitals from the oxygen. And that side-to-side overlap will form the double bond, and that side-to-side overlap is a pi bond. So whenever you have a double bond, remember that one of those bonds will be a sigma right over here, while the other one will be a pi bond. But the most important thing is that there are only 3 domains around the carbon. So a structure that has 3 domains will be sp2 hybridized. Now let's take a look at sp. Now notice how I showed you that carbon could be sp3 hybridized, like in methane. And in the previous example with the 2 hydrogens and the oxygen, it was sp2 hybridized. Same carbon, but different hybridizations. Now I'm going to show you how carbon can be sp hybridized. So in sp hybridization, notice only one of the s's, well, the only s and one of the p's are going to merge and hybridize, and you're going to leave 2 p orbitals unhybridized. The 2 atomic orbitals that hybridize will form 2 molecular orbitals. That's the theme. 2 atomic orbitals makes 2 molecular orbitals of equal energy, degenerate. So we have 2 molecular orbitals, and we have 2 unhybridized p orbitals. You're going to see that this structure here would be responsible for forming a linear shape. I'm going to use the molecule C2H2 in a moment. When you're linear, you will see that the bond angle will be 180 degrees. So the atoms, notice it uses hybrid orbitals for the sigma bonds or for lone pairs, and it will use the non-hybridized orbitals to make pi bonds. Okay, usually, and the example I'm going to show you, especially a linear structure like this, you'll have 2 sigma and 2 pi bonds. And I'm going to go ahead and show you here what happens. So the 2 atomic orbitals, the s, one here, the s here, and the p are going to get together. So 2 atomic orbitals will form 2 molecular orbitals, as you can see here. When you merge them together like this and they merge, notice you will form the sp hybrid will look like this. Notice the linear arrangement, it's 180 degrees. And this is what it would look like. Notice that the carbon has 2 domains around it. Either carbon, picture this one as the central atom. It has one thing on this side and one thing on this side. And you could have done it easily the other way around. It doesn't matter which carbon you pick. If you pick this carbon, it has 2 domains around it, whichever one you pick. So when you have 2 domains, not only are you linear as far as electron geometry, you're also going to be sp hybridized. Now look at this. Let's look at the carbon on the left here. So notice here's one of the domains, okay? And then the other domain is forming a sigma bond. You got a sigma bond on the left with the hydrogen. You got a sigma bond with the other carbon, but there's a triple bond. Now remember that in sp hybridization, 2 of the p bonds did not hybridize. Now I don't know if you could tell with this picture very well, but Notice there's a triple bond. One of the bonds we know is a sigma bond between the two carbons. One of the p unhybridized orbitals, okay, which we can say it's, let's say, this one over here and over down here, I guess these two, if you could see that very well. Those two p orbitals overlap side to side, forming a pi bond. But remember, there's a second unhybridized p orbital, and that second unhybridized p orbital will also overlap side to side, forming another pi bond. So when you have a triple bond, one of those bonds is a sigma, and the other two are pi bonds. Each one is formed by the side-to-side overlap of that unhybridized p orbital. So linear has two domains, and the hybridization is sp. So notice how I showed you how carbon can either be hybridized sp in linear, sp2, which would form something trigonal planar, or sp3, which forms something tetrahedral. Now we can also form an sp3d hybridization. Notice there are 4 domains here. Five domains. An S, 3 P's, and a D. That is 5 atomic orbitals getting together. So if 5 atomic orbitals get together, you guessed it, you will make 5 molecular orbitals. So atoms with 5 electron groups around it form a trigonal bipyramidal electron geometry. Shapes include seesaw, T-shaped, or linear. Angles are either 120 or 90 degrees. And one of the empty d orbitals from the valence shell is used to form the hybridization. The other d orbitals will remain unhybridized. You could see here an example. This is sp3d hybrid. This one is trigonal bipyramidal, and look what happens. Here is the S, the 3 P's, and one of the D's. Remember, there are 5 d orbitals. Notice these 5 atomic orbitals merge together and form 5 molecular hybrid orbitals. Each one is sp3d hybrid. The other 4 D's result, basically they stay unhybridized. Okay? So this is how a trigonal bipyramidal geometry is formed using hybridization. Then you also have the octahedral, and in this case you have an S, 3 P's, and 2 D's merging together. That equals 5 atomic orbitals, and when they get, 6 atomic orbitals, and when they get together, you're going to form a molecule that has an electron geometry with 6 domains, which is the octahedral electron geometry. Shapes also include square pyramid, square planar. Angles will be 90 degrees. You could see this example here. There are 6 domains. All of these are occupied by bonding or by an actual atom. But remember that a domain can also be occupied by a lone pair. And again, it will use 2 of the empty d orbitals to form the hybrids. The other d orbitals will remain unhybridized. If you look here, here are the 6 atomic orbitals merging together. And again, the theme goes like this. 6 atomic orbitals will form 6 molecular orbitals. And they are all of equal energy, represented in the purple there, which is the word degenerate. And then notice that 3 of the d orbitals remain unhybridized. So that would be the electron geometry when you have 6 domains. The hybridization would be sp3d2. So here, at the end of the day, this is what you really want to remember. I have a trick for you to remember this. Notice that linear means you have 2 domains. The hybridization for linear is always sp. How many letters does sp have? 2. So 2 letters, 2 domains. 2 domains is linear. This is a good way to remember it. If you have 3 domains, you're trigonal planar. Notice the hybridization is sp2. 2 P's and an S adds up to 3. So if you have 3 domains, you are trigonal planar. Look at tetrahedral, same thing. sp3, you count the 3 P's and the S, that counts as 4. The shape or the electron geometry with 4 domains is tetrahedral. So all tetrahedrals will be sp3. hybridize. Whether you are a regular tetrahedral bent like water, okay, or like ammonia, which is trigonal pyramid. And I'll write water here for a moment. If you have 4 domains, that oxygen has 4 domains. You have 1, 2, and then 2 with lone pairs. That oxygen would be sp3 hybridized. Okay, remember, hydrogen cannot hybridize. Hybridization always has to do with the central atom, not the peripheral atom. So keep that in mind. When we talk about hybridization, we're referring to the central atom. And then the last two, sp3d, if you count that, there are 5 letters there, an S, 3 P's, and a D. The electron geometry with 5 is trigonal bipyramidal. So all trigonal bipyramidals, which includes also seesaw, T-shaped, linear, that have 5 domains, they are all sp3d hybridized. And if you're sp3d2, that means you have 6 domains when you count the letters, and that will be for the octahedral electron geometry, and that will also include square pyramidal and square planar. So this is a great way to remember. If they ask you what type of hybridization, look at the central atom, count how many domains, and the letters will match. So if you're tetrahedral, you got 4 domains. So the electron geometry with 4 domains would be will be tetrahedral, but the hybridization will be sp3, which has 4 letters equaling 4 domains. Lastly, there are some limitations of valence bond theory. Notice that valence bond theory predicts many properties better than just regular Lewis theory, such as bonding schemes, bond strengths, bond lengths, and bond rigidity. But valence bond theory presumes that electrons are localized in orbitals on the atoms in the molecule. It doesn't really account for delocalization, which is what you would see when we're talking about resonance. So that's one of the limitations of valence bond theory. It doesn't really explain delocalized electrons very well, which is what you would see when there's resonance going on. And then there are still many properties of molecules it doesn't predict perfectly, such as the magnetic behavior of oxygen. So hopefully this video gave you a good overview of the connection between the electron geometry and the type of hybridization involved in that central atom. Okay?